Alright, so we're going to look at another triose that we call dihydroxy acetone. Alright, like earlier mentioned, I just want to write its straight chain, okay, so that we may actually see what exactly it looks like. Alright, so this is dihydroxy acetone, and as you notice that the carbonyl group is on carbon number 2, hence given the name dihydroxyacetone. So this is dihydroxy acetone. So when you look at this at the end of the name of a molecule, you already know that it is going to be a ketone group. A ketone group because the carbonyl group is on carbon number 2. Alright, the next part that we're going to talk about is pentoses. Alright, so look at what we call pentoses. So what exactly is a pentose? From the name itself, you can tell that a pentose is a 5-membered carbon chain or carbon ring. So a pentose is going to have 5 carbon sugars with the formula of C5H10O5. So the examples that we have ribulose, we have ribose, and lastly we have deoxyribose. Okay, so these are examples of pentoses that we have. Now you need to note that these, for instance, the ribose, okay, I'm going to look at the function. The ribose is used, the ribose and deoxyribose are sugars that are used in nucleic acids. Okay, these are nucleic acids. Then the ribulose, we'll also look at its function. So we'll look at its function right there, and you discover that its function is, it's important in photosynthesis. Okay, so photosynthesis. Alright, so ribulose is usually used as an carbon dioxide acceptor. So this is a sugar that is used to accept carbon dioxide during the process of photosynthesis. When you look at, to take you back to ribose, ribose is a sugar that is found in RNA. Deoxyribose is found in DNA. Alright, so these are the pentoses that we have in nature. Okay, next we're going to look at hexoses. Okay, but before we look at hexoses, I want us to give more clarity about the ribose and deoxyribose. Alright, so having said that, now that we know that the RNA and DNA use pentose sugars, okay, they have pentose sugars in their structure. What we're going to notice is that when you look at their structure, they just differ at one point. So if this is ribose, let's just draw it, you notice the difference. So this is 1, 2, 3, 4 and 5. Okay, so on carbon number 2, you notice that the oxygen atom is present. So this oxygen is present. So the oxygen atom is present in ribose. Okay, but when you look at deoxyribose, you notice something as well. So you notice that this oxygen group is absent on carbon number 2. Okay, it's going to be absent. Alright. So on carbon number 2, we don't have oxygen. Hence, this is why it gets its name. Deoxyribose. Okay? The deoxy meaning the oxygen group has been removed. Okay? That's what that's simply meaning. So regardless, whether it's an open chain, whether it's a ring form, on oxygen number 2, one will have an oxygen group and one will not have an oxygen group. So what we notice is that in order for this ribose or deoxyribose to form a ring, the carbon number 4, remember we count from the top. So let me just highlight. This is carbon number 1, 2, 3, 4, 5. So the carbon number 4, this carbon that you're able to see here, combines with carbon number 1. So this carbon combines with carbon number 1. So we're trying to make a ring, a straight chain. Okay, so it combines with carbon number 1 of the open chain, and both ribose and deoxyribose forming the formation of a 5-membered ring. So when this carbon number 4 binds with carbon number 1, they will form a straight a ring structure such as this. So it's going to be a 5-membered ring. Okay, so we call these rings that are 5-membered as Furanus ring, meaning it's 5-membered. Okay, so this is how it comes about. When this bends and it connects with that other carbon atom on number 1, it's going to form a Furanus ring. So we have an OH group here and an H and another one there. Okay, so this is what is happening. Okay, another thing we need to note is that the oxygen on carbon number 4, this oxygen that we're able to see right here, it links with carbon number 4 to form a closed ring. The oxygen on carbon in this carbonyl group that you can see here, this is the oxygen that we are able to see right here on the ring. Okay, this is the oxygen that is being observed. Okay, so this carbonyl, the oxygen on carbon number 1, combines with hydrogen group on carbon number 4. So this oxygen combines with the hydrogen on carbon number 4 to form an OH group, which is above. So these two combine to form an OH group. Pardon me. So this oxygen group. Alright, so we have oxygen there. So there's this OH group. This OH group is coming about because the oxygen on carbon number 1 is combining with the hydrogen on carbon number 2, therefore making an OH group which faces up. Okay, and when the OH group on carbon number 1, so this is 1, 2, 3, 4 and 5. So when the OH group is facing above, we call this an alpha OH group. Okay, so because of this arrangement, you find that this carbon number 1, so like you can see, there is a carbon atom here. It's going to be bonded to 4 different things. So it's combined to the OH, it is connected to the H, it's connected to the oxygen, it's connected to another carbon. So when carbon is combined to 4 different elements, we call it a chirocarbon. Okay, it's going to be called a chirocarbon atom. Alright, this is what we mean, that it's called a chirocarbon. So because of this, we're going to have what we call alpha and beta forms of this, or rather stereoisomers. Okay, so stereoisomers are coming about because it's either the OH group is facing down or on top. So let me just highlight that. So when the OH group faces down, it's a beta. When the OH group faces up, this is an alpha. Okay, So we're going to talk about a hexose sugar next. We'll look on hexose sugars, right? Alright, so when you look at hexose sugars, it means they have 6 carbon atoms in them, and their formula is going to be C6H12O6. Okay, examples that we have glucose, we have fructose, we also have galactose. Okay, so these are a direct source of energy. Okay, because remember, these are monosaccharides. They're a direct source of energy, and they can be oxidized during aerobic respiration or tissue respiration. So glucose is the most important respiratory monosaccharide, like we have been talking about. And when you look at these hexoses, these are the only ones that can be used to synthesize disaccharides. Okay, so when you look at the disaccharide, it can only be synthesized when we use hexose sugars. You can't use a pentose or a triose to make a disaccharide, or a tetrose. That's not possible. Okay, that's why you are only able to make disaccharides using these hexose sugars. Alright. Okay, so the next thing that we're going to talk about is that we have, when you have one monosaccharide, okay, you can have one monosaccharide, you can have two monosaccharides, so it's going to be called a di. When you have 3, or rather 2 all the way up to 10 monosaccharides, it's going to be called oligosaccharides. When we have more than 10, so 10 to infinity or greater than or equal to, we're going to have a polysaccharide, meaning this atom or other molecule has so many glucose atoms in it, or rather glucose molecules or monosaccharides, since monosaccharides are the basic structural unit of all monosaccharides. Okay, so I want us to look at what we call hexose isomers. Okay, so when you look at these isomers, have molecules that have the same number, same molecular formula, so they have same molecular formula but different arrangement of atoms. Okay, so they have different arrangement of atoms. So now we have different types of isomers. The first one that I'll talk about is optical isomers. Okay, I'm sure you remember that I said something about optical activity. So in these optical isomers, we have 2 types. It's either one is D and one is L. So we have L and D isomers. The next type of isomers that we have are called stereoisomers. Okay, so stereoisomers. So these isomers have the same molecular formula, but they differ in spatial arrangement. So they differ in spatial arrangement of atoms. So this is to tell you that it's either one is going to be alpha D glucose, for instance, could be alpha or could be beta, meaning the OH group can be at the top or it can be at the bottom. The next we have structural isomers. Okay, so these structural isomers, notice that they'll have the same molecular formula, but they'll differ in terms of the structure, such that it's either one is a ketose, one is an aldose. So structural is either one will have an aldose or an aldehyde, or a ketose or a ketone rather. So it can either be a ketose sugar or aldose. So this is what we mean when we say these are structural isomers of each other. Alright. So having said that, we talk about glucose. Okay, so when you look at glucose, glucose is oftentimes referred to as grape sugar. So this is glucose. It is also called grape sugar. Okay, it's a simple monosaccharide found in plants, and it's actually important for the process of photosynthesis, okay, and the fuel in cell respiration. So we have cell respiration and photosynthesis. Okay, this is what we use glucose for. So the reason why glucose is able to form hydrogen bonds, or rather the reason why it's soluble in water, is because glucose forms hydrogen bonds. So it forms hydrogen bonds with water molecules. So like you can see, in the first place we mentioned that these monosaccharides are actually soluble, okay? The reason why is because it forms hydrogen bonds with the water molecules. So a hydrogen bond means oxygen will combine with the hydrogen on a different water molecule, and so on and so forth. Okay, so having said that, the open chain of glucose is an aldehyde. So when you talk about the structure chain of glucose, you notice that it is an aldehyde. So this is an aldehyde. So this is to tell you that it has a carbonyl on carbon number 1. Okay, so carbonyl on carbon number 1. Alright, so this is what you'll find on glucose, and the chain continues since there are 6 of them. Just a minute. Okay, so when you look at this chain, 1, 2, 3, 4, 5, and 6. Notice that glucose is an aldehyde group. Okay, carbon number 1 has the carbonyl group. So what happens for glucose is that, first, before we write the mechanism, I just want us to see something. So what happens for this open chain to become a ring chain? The carbon number 5 is the one that to connect with carbon number 1. Okay, they will combine. So the carbon number 5 in the open chain is going to give us a 6-membered ring. So this one gives us a 6-membered ring that's called pyranose. Okay, so pyranose meaning it's 6-membered. It's a 6-membered ring, and because of this, from a straight chain into us making a ring chain, you'll find that the OH group can either be at the bottom or at the top, like we said. So we can have alpha isomers or beta isomers. So the existence of these alpha and beta atoms, it leads to a formation of many dimers. A dimer meaning you have 2 sugars that are bonded together, and it can lead to polymers of glucose. So meaning you can add so many glucose molecules to the glucose itself in order to come up with a very large molecule. So glucose is used as a source of energy, like we said, and glucose is the power for reducing sugar. Okay, so we need to highlight this. Why is glucose a powerful reducing sugar? Alright, so it is a powerful reducing sugar. So when you look at this, this is to tell you that this carbonyl group on carbon number 1 is what enables it to actually be a very powerful reducing sugar, because remember, the functional group, okay, is the one that determines the reactivity of this atom. So it is this aldehyde group that is able to react, okay, and enable glucose to be a very powerful reducing sugar. Yes, so when you look at the L isomer, before we go to that, glucose has isomers such as D and L isomers, okay, but then the D is less common. So the D is common, sorry. So the D is common, but the L is less common. All right. So the reasons why the L isomer is less common, it's because the body naturally doesn't have enzymes that can break down this L glucose. Hence, that's why it uses an alternative by just using D glucose. All right. So the body has no enzyme for this type of glucose. So living organisms cannot actually use the L glucose as an energy source because they don't have the enzymes to break it, like we said. Alright.